So this is to do with the AS atomic structure. We're going to look at atomic structure today. Do please stop me and ask questions if there are bits that you don't know about. So we start off with the basic structure of the atom. Now we looked at this when we did electric fields, because what we did was we looked at Rutherford scattering, the alpha particle scattering. It went from probably just about 120 or so years ago. What we had was called the plum pudding model. So the plum pudding model involved a positively charged sort of atom with lots of negative bits in balancing the positive charge out. It was very quickly, through the alpha scattering experiment, discovered to be not fully correct. And so the alpha scattering experiment, which is on a previous YouTube video, so please do have a look on my channel if you can't remember alpha scattering. The alpha scattering experiment proved that it was wrong and came up with the idea of a positively charged nucleus being orbited by negatively charged electrons. And these electrons, they worked out, they had very, very little mass to them. Most of the mass of the nucleus, of the atom, was concentrated in the nucleus, which was far smaller than the atom. To give you an idea, the size of an atom is somewhere around about 10 to the power of 10 meters, 10 to the power of minus 10 meters across. The nucleus was more like 10 to the power of minus 15 meters across. So it's about 100,000th of the size of the actual atom itself, but all the matter was concentrated there. The problem with that was that it wasn't just one type of particle in here. Rutherford knew this because he measured the specific charge, which is the charge to mass ratio. Specific in physics means per unit mass. And it wasn't constant, which would imply that there's more than one type of particle. So Rutherford predicted the idea about neutrons, but it was actually, I'm not going to go into the experiment because you don't need it, it was actually the work by Chadwick, who worked out that actually inside the nucleus, so if I draw something like helium, there were neutral particles, which are black, and positively charged particles, which are put white with a cross in the middle, being orbited by those electrons. So this model was not quite spot on. This is the nuclear model of the atom. So that was the basic sort of history behind how we know about the existence of nucleus, neutrons, and protons. And the idea was pretty simple. Basically, there are three particles: neutrons, protons, and electrons. And they all had a particular charge. Now, as we've done electric fields, I can say Q for charge. The charge of the neutron is 0. The charge of the proton was plus 1.6 times 10 to the minus 19 coulombs. Electrons minus 1.6 times 10 to the minus 19 coulombs. Which is all very well and good, but really we need to think about sort of more convenient numbers, because we also found out the mass of each particle. That was quite a low mass. The protons had the same, proton neutrons had about the same mass. Electrons were much lighter, but again, it was a very tiny number. So what we do is we look at the relative charge and the relative mass, which is always relative to the proton. So if we think about it, a neutron had the same mass as a proton, so its relative mass was 1. Its charge obviously was still 0. A proton, well, relative to a proton, obviously it'd have a charge of 1 proton charge and 1 proton mass, because it's a proton and we're comparing it to protons. And then you have electrons, which have a relative charge of -1. It's equal and opposite, as you can see, and had a relative mass, well, it's about 1 over 1,800 or 1 over 2,000, but we usually call it 0 because 1/2000 is such a small number that we generally don't bother with it very much. Now, that was all very well and good, and we could actually then start to think about what that means in terms of how we represent atoms. So, for example, if I took helium, now I'm going to take an ion of helium here and say +2, okay, to give you an example. And I'm going to compare it with ordinary helium. Now, helium, stable helium, has a relative mass of 4 and a relative nuclear charge, what we call the proton number. Proton number, sometimes it's called the atomic number, of 2. Now, what that means is that if you've got helium-4 here, what that means is basically you have 4 particles in the nucleus. Whoops, 4 particles in the nucleus, and we know that 2 of them were protons. So 4 particles minus 2 which are protons means you must have 2 neutrons. Okay. Now what we have here is what we call the ion number, or the ionic charge. Now this one, obviously, it should have, if we've just got helium here, just as neutral helium, we know that we have 2 neutrons, 2 protons, and as there's no charge, the relative charge of the nucleus is going to be 2 because there are 2 protons. So as a result of that, what we have to do is we have to think about what happens to balance it out and make it neutral. Well, the way to make it neutral is if the charge is going to be 2, because you've got 2 protons, you've got to have 2 electrons. With the ion, you've got a charge of the nucleus of +2, so that would imply no electrons. So that is just a helium nucleus, whereas this is a helium atom because it's not ionized, it's got no charge. So to give you another example, if I take a different one, if I take carbon. Now this standard most stable form of carbon is called carbon-12. So the proton number, if you think about it, is what tells us what element we have. If you change the element, if you change the proton number, you change the element. Why? Because in order to have an atom of carbon, if you've got 6 protons in the nucleus, you've got to have 6 electrons orbiting the nucleus. If you've got 6 electrons orbiting the nucleus, well, the electron configuration, how the electrons are actually sort of arranged around the nucleus, dictates the chemical properties of a particular substance. So as long as you've got 6 protons, you'll always have 6 electrons orbiting the nucleus, so all the carbon will behave like standard carbon atoms. Okay. Now, obviously, if we've got carbon-12 here, if that means we would have 12 particles minus 6 implies that you've got 6 left, 6 neutrons. Okay. Now, the number of neutrons, number of protons is not always the same as the number of protons. So, for example, if you've got carbon-14, okay, it's a radioisotope of carbon. Here you've got 14 particles minus the 6 protons, leaves you with 8 neutrons. Okay, it's an isotope. It's an isotope of carbon. So what that means is that you've basically got 6 protons, 8 neutrons, still 6 electrons, because you have to balance the protons and electrons to have a neutral atom. We don't really do much with ions in physics, certainly not in A-level physics. You might come across them when you're talking about charged particles in the electric fields topic. That's about it, really. So here we had 6 protons, 6 neutrons, 6 electrons. It's the number of neutrons that dictates the different isotopes. So if you've got 2 isotopes of carbon, the way to define an isotope of an atom is the same number of protons, but a different number of neutrons. And that's how we define what an isotope is. So that's all very well and good. Now, why do we have a notation like this? Well, it's very simple. I'm now going to look at radioactive decay. I'm going to combine the topics simply because we've covered this briefly before, but also because I think it's probably the best way to actually explain it. So I'm going to do like a case study, and we're going to learn some new physics through that particular case study for a moment. So I'm going to take carbon-14. Now, carbon-14 is radioactive. Is actually a radioactive isotope. It's what we call a radioisotope of carbon. It decays, we happen to know, by what's called beta minus emission. So we're going to look at beta minus, what we call a decay. Now, first of all, radioactive decay is random. If you think about it, if you take a coin and you toss a coin, you never know whether it will land heads or tails, unless you're very, very skillful at tossing coins, of course. What happens, what it is that an individual atom could decay at any moment. It's a random event. Not to be confused with spontaneous. Spontaneous. A spontaneous means it's not affected by anything. So unlike a chemical reaction in which, say, you're reacting an acid with an alkaline, if you increase the temperature of your acid and alkali solution, then you should get a more rapid reaction. If increasing the temperature of, say, carbon-14 won't make it decay any faster or slower. It's completely independent of things like temperature, concentration, and that sort of thing. Really, the only thing that affects the level of radioactivity coming from a sample is the amount of the sample and how long it's been there for. When we do half-life next year, you'll understand a little bit more about that. So if we think about it, what's actually going on? Well, the thing that's going on is we're starting off with carbon-14, and it's unstable, okay? It wants to break down, it wants to change. So what it does is it emits a beta particle. Now, a beta particle is essentially an electron. Now, if we go back and we think about it, what's actually happening? Well, if we look at the atomic number or proton number and the relative mass, we assume the relative mass of an electron is 0 and its charge is -1. So we have to add it up, and this is why we have this particular type of notation, because these numbers are conserved. In other words, the same before and after, in the same way that momentum is conserved for isolated systems. So we started out with 14 neutrons and protons. You've got to end up with 14 neutrons and protons. But the charge is going to be different because you've got -1 here. So to get 6 from -1, you've got to add 7. 7 plus -1 makes 6. So we end up with nitrogen instead of carbon. And that's actually what happens naturally. So we're going to come back to beta minus decay because something else also happens. Now, if we look at all the different types of decay, we also have alpha decay, where you might take something like uranium-238. It emits an alpha particle. An alpha particle is 2 protons and 2 neutrons, okay? So if it's 2 protons and 2 neutrons, its relative mass is going to be 4, because 2 plus 2 makes 4. the charge or proton number, I always call it proton number because it tells me how many protons I've got. So I will say that's going to be a 2. As these numbers are conserved, they have to be the same before and after. So you've got to add up to 238. So that's 234 because 234 plus 4 makes 238. And you've got to have 92 at the end, so you must have 90. So again, we've changed the proton number. So we've changed the element, and that's actually thorium. You don't have to know that thorium has an atomic mass of 90. You're given that in any particular question. So if you've got an atomic mass of atomic number of 90, you don't have to know that that's thorium. But you do have to know the atomic mass and proton number for alpha and beta particles. Okay. And then we have gamma decay. Gamma is just basically a photon. It's a particle. It's a little packet of energy, a particle of light. And an example of that might be, say, cobalt 60, which will become still cobalt 60, but the nucleus is set up to have a little bit of energy in it, and all that happens is the particles inside that nucleus kind of drop down to a less energetic sort of configuration. So we know it's got a charge and a mass of 0 because it's light. Light doesn't carry mass. Light doesn't have a rest mass. Light doesn't have a proton number. There are no protons or charge in particles of light. So gamma decay is probably the simplest one to predict. Alpha decay, we go back to alpha decay. If you were to look at this, if you think about it, the uranium changing into thorium is going to be the same no matter which uranium atom, uranium-238 atom it is. So it's going to, if we look at if we emit lots of alpha particles with a large sample of uranium, if we count the number of particles versus the kinetic energy of that particle, you'd expect them all to be pretty much the same. There might be a few very, very minor differences, but actually we'd expect one energy. So because you've got the same thing happening again and again. So if the same thing happened again and again, the kinetic energy of the alpha particle is always going to be about the same. There might be a few differences, but not many. Or you would expect at least the same or some discrete values. Beta decay, it's not the same. If we were to look at the number of particles versus the kinetic energy of the beta particle, it's sort of a spike. It's sort of a range almost. It's not a spike. So what's actually happening is that for the same decay, we're getting a range of energies. And that doesn't make sense unless some energy is being lost elsewhere as well. So what must be happening? There must be something else emitted that could have a range of energies. It also conserves momentum as well. So if we think about it, if we've got the beta particle, there must be something with no mass and no charge. But it's got to have, well, no relative mass, but it must have some mass because it has to have some kinetic energy. So it's some weird particle. It's neutral. It's a neutral particle, and it is very, very small with almost no mass. Now, a lot of particle physics follows patterns with naming, and the particle is actually an electron neutrino. It's different to a neutron. An ohm is a particle. An ENO is a very, very small particle. So it's a very, very small neutral particle. Now, the other problem with this is they also discovered pretty quickly that actually it's kind of an opposite mass particle. It's actually what we call an antineutrino. And it starts to give us a few problems. It's behaving like an opposite to a neutrino. Neutrinos can be emitted by what's called beta plus decay. So if we take something like, let's think of a good example. If we take something like nitrogen 18, we know we've got 7 protons, therefore 7 electrons, And 18 minus 7 would have 7 neutrons. It'd be quite an unlikely one. It'd be rather unstable. I don't think you'd be able to collect much in nitrogen 18, really. But if you've got lots and lots of neutrons, what actually happens is that we emit a positively charged particle called a positron. Now, when we need, sorry, my dyslexia is not good at the moment. When you actually emit a positron, it has all the opposite properties to an electron, but people didn't know about antimatter. So it's the exception to the rule. It's actually an anti-electron. It's an anti-electron. So it's got all the exact opposite properties. So whereas an electron under mass of 0, well, the opposite of 0 is still 0, but it has a charge, the electrons have a charge of -1, this has got a charge of +1. So again, the numbers need to add up. So 18 carbon and you'd have maybe 6. This is obviously not really a feasible interaction, but it's a good example. The point is that what actually happens during beta plus is that a proton becomes a neutron, whereas in beta minus, what's actually happening is a neutron becomes a proton. So as we started to build the picture, we can start to think about what's actually happening with all the other particles. And so you end up with the neutrino being emitted as well, okay? So what's actually happening? Well, what's actually happening inside the nucleus, as we said, in beta minus decay, a neutron has clearly become a proton because the neutron number, particle number stayed the same, but the proton numbers increased. So the number of neutrons here is 1 less, and the number of protons is 1 more. So the neutron's got to somehow become a proton, and it's done it by emitting the beta minus particle and, of course, the antineutrino. Okay, the numbers still add up because you've got 1 and 0, 1 and 1, 0 and -1. It still adds up. So what's actually happening inside here is you also have a proton becoming a neutron. It's got to emit a positron and again a neutrino. Okay, so that is the process behind that radioactive decay. As we move on, we start to really sort of think a little bit more about what goes on during these decays and what the properties of these 4 particles are. So if I start to look at properties of alpha, beta, and gamma, if I look at alpha, for example, we know we've got alpha, beta plus, beta minus, and gamma radiation. You do need to know the symbols. You do need to know these symbols. You need to know what each of these are. So what they are is alpha is a particle with two protons and 2 neutrons. Beta plus is a positron. Beta minus is an electron. And gamma ray is basically a photon, a high energy photon or particle of electromagnetic radiation. As we start to then think about the properties, we know that they've got a relative charge, and we're going to look really at relative charges and masses here. Why? Because to actually work out the actual charge and masses create some fairly long numbers. Then you do need to know the relative charge of any, the actual charge in coulombs or the mass in kilograms. Again, in an exam, that's on your formula sheet. So the charge is +2. The charge of beta plus is +1, -1, and 0. And with the mass, it's again, this is going to be a mass of 4, a mass of 0. We call it 0. We know it's 1/2000, but we kind of make it easier to work out by just sort of approximating it to 0. Now, each of these particles have different properties. We knew about the properties of the particles, I think, before we knew really what they were. So the best way to think about it is imagine you've got a radioactive source. Radiation symbol looks something like that. So we've got a radioactive source. Now, this could be emitting all sorts of different particles. This could be emitting alpha. It could be emitting beta. Now, because these two particles are the same, but they're opposite, if you know what I mean, they're both sort of derived from very, very similar sort of massive particles. I'm just going to say beta. And we've got gamma. Now, the way that we need to understand about it, what we need to do is we need to understand what's actually going on here. So if we took some thin paper, whoops, try to spell it right. If we took some thin paper, the alpha particles would actually be stopped by it. The beta particles wouldn't be sort of changed very much by it, and the gamma rays gamma rays would go straight through the paper as well. But if we took a piece of aluminium, a few millimeters will do, what you find is the beta particles are pretty much stopped by a few millimeters of aluminium. Obviously, they'd also stop the alpha particles, but the beta particles, the beta radiation is stopped by aluminium, but the gamma rays still go straight through. You actually need a fairly thick piece of lead to actually even attenuate slightly, to even attenuate the gamma rays. Some gamma rays would still actually go through. So when we look at penetration, we know it's stopped by a few millimeters, so it's the least penetrating. Alpha particles are the least penetrating. Beta particles are stopped by a thin sheet of aluminium or something similar to that. Okay, same as above for beta minus. But gamma rays are the most penetrating. Okay, so what we're actually looking at here is the idea that there's kind of an order of things. The way I think about the next part is I think about traffic. I drove to work this morning. I drive for an hour every morning to get to work. So let's think about what alpha particles are. Well, alpha, beta, and gamma rays are. Well, if we think about it, the alpha particle I think of as being like a big lorry. The beta particle I think of as being a bit like a car. And the gamma ray I think of as being a bit like a motorbike. Okay, I can't draw motorbikes very well, but if you think about it, if you're trying to get through heavy traffic, or in case of the particle matter, if you've got a big vehicle, it's very difficult to get it through the traffic, and as a result, it has to interact a lot more. It seems that the lorry seems to have to interact with atoms a lot more. Now, what that means is that as that's to interact, it's more ionizing. The beta particle is less ionizing. It can sort of nip in and out the traffic, but the gamma ray motorbike is the least ionizing. So as a result, the gamma ray can get through the traffic. The motorcycle can get through the traffic with the fewest interactions with anything. So it then tells us an order of ionization of atoms. So if we think about it in terms of safety, well, in terms of safety, if we think about it, if you've got some DNA inside our cells, is a double helix, okay? And they're basically just molecules that are bonded together. Now, if you get an alpha particle doesn't get through very much. It's very easy to shield, but if it does hit an atom, if it does hit one of the atoms or one of the molecules in your DNA, it will ionize it, okay? So alpha particles are very ionizing. So a source of alpha radiation, if it gets into contact with your DNA in your cells, it will damage them to, it'll be more damaging. Beta particles, less so. Gamma rays don't really ionize very much at all, so actually they go straight through you. They don't really interact, which means it's the least harmful. So alpha radiation is most harmful to your health, and gamma radiation is actually the least harmful. It still interacts, but it interacts with, interacts less than, ionizes less than the alpha particle does. Okay, so high doses of gamma radiation are still harmful, but in terms of the amount of radiation, all things being equal, gamma radiation does you less harm than absorbing alpha radiation. The advantage with alpha radiation, though, is of course it's not very penetrating. So if you think about it, the top layer of your skin is pretty much dead skin cells. What actually happens is that the outer layers of skin will absorb all the alpha particles, so that it doesn't really get below your skin. Gamma radiation will go straight through you, but it can ionize some of your cells. So gamma radiation, for example, would go all the way through my hand. Beta radiation would penetrate away into your body, but not all the way through. So we can start to think about it in terms of the level of harm produced. If we start to look at the behavior of the particles, another thing to look at with behavior of the particles is to look at what happens as they pass through an electric field. Now, you did electric fields before, so imagine you've got a positive here and a negative plate here. If you've got an alpha particle will deflect away from the positive towards the negative. Now, it's got a very large mass, so it takes quite a lot to actually get it to deflect. A beta particle has got only half the charge, but much less mass, so it will be deflected and attracted to the positive plate much more readily. However, gamma rays would go straight through. Okay, so that's one way that we can separate out the different sort of particles. So that's the overview. So what are we sort of taking home from this? Well, we know from our summary, we know about the structure of the atom. We know about the structure of the atom, what's called the nuclear model. We know about the notation. Okay, for example, carbon 12. We know about alpha, beta plus, beta minus, and gamma radiation. We know about neutrinos. We know that neutrinos exist, and we know that neutrinos are emitted in beta plus and beta minus emission because there's some leftover kinetic energy which has to be accounted for somewhere. Okay, we know with the types of radiation, we know about the properties. We also have learnt some of the key words. Some of the key words that you do need to know the definitions of. So those key words are words like the easy ones that we all know, the nucleus, ion, they're pretty easy. You need to know what an isotope is. An isotope, you remember, is an atom with a different number of neutrons but the same number of protons. We know other key words. We know about, we have to know what a neutrino is. Okay, you have to know the properties of the neutrino. We know, if we think about it carefully, we know the words spontaneous and random. Okay, we know you have to know what those words mean. Okay, we know what ionization is. You know what it is when an atom becomes charged. It's the electrons. The electrons are either added or removed. Okay, and you need to know. Whoops, try and spell it right. What penetration or penetrating properties are. Okay. So those are the key words that you do need to sort of know about that I've covered today. As I said, this shouldn't be relative. This shouldn't be particularly new, but will help you with revising the topic. As I said, you have an exam next week. You have your multiple choice on Monday, which you can pick up from Show My Homework, and then you have your written answer paper on the Wednesday, which again you can pick up from Show My Homework. Any questions, Owen?
Yeah, Gary, you said the tests wouldn't have topics, wouldn't be from fields. So what topics would the test be from?
Basically, it's everything else that we've studied. So
Right.
if you think about it, we've got measurement and units. We've got forces and motion, energy and work. We've got vectors, okay, which links to force and motion and energy and work, okay, but vectors are important. What else have we got? We've got, you've then got your circuits, which include things like current, potential difference, EMF and internal resistance. They contain, there might be a little bit on electric fields, but just uniform fields. Okay. You might get a little bit on potentiometers in PD. Also, you've got the nuclear physics topic.
End of period 1.
And finally, you also need to know everything about waves. Okay? So that's properties of waves, stationary waves, whoops, electromagnetic spectrum. Okay, that sort of thing. Okay, is that all right?
Yes, yeah, thank you.
Okay, any other questions?
No.
Okay, well, I'll stop recording there. I've set you a good Seneca revision task for the nuclear physics topic to do this afternoon. So please have a go at that. The link to that is on Show My Homework, and I will see you next time.